Thank you very much, Rainer, for the introduction. I want to start this session with a thought experiment. The rule is, if you know the answer, you cannot participate, of course. Let's start it. You have just received $1 billion US. Congratulations. And you are very extremely eager to make an impact for the 450 million people living in Europe. You want to bid for the environmental bill for 1 month of EU travel caused by all the passengers. Let's say in 2025, because that's when we say that the traffic level will be back to pre-COVID. And you can keep the rest of the money for yourself. And in order to do so, I will start with 10 million. Okay, and each step, if you raise a hand, we will raise up to 20 million, for example. You can also shout out a number. And the money you have is 1 billion. So let's start bidding. Who want to start with 10 million? Okay, 20 here. Is there a higher bidder? You can go wider, eh? 30. You can make it 40, 50, 60, 70, 80. Be aggressive. 90. 90 one time. 100. 100 one time. Is there any online? 100 million twice. 110. 120. 130. 40. 50. No, 200. Okay. 200 one time. 200 twice. 300. Okay. 300 one time. 400. 400. Okay. Have higher bidder. One time. Second. Third. Okay. 400 million. Remember the number, please. The title of this presentation is called Evaluation of Aviation Emission and Environment Costs in Europe using open data, open sky data, and OpenAP. On behalf of my co-author Irene Dituzzi, I would like to present the result that we have done in this study. So both myself and Irene, we just recently started a research lab in TU Delft, which is called Sustainable Aviation Lab. So we want to take a systematic approach to address the impact of aviation. And we want to make all the research open and accessible for every stakeholders on the Earth. So as most of you know, that a lot of my work is centered around ADS-B. During my PhD, I developed something called OpenAP. It is allow us to make a fully open model to assess aircraft performance. And one of the important part is a fuel flow model. And over the past few years, ourselves and a team of master students, PhD students, have been helping us to make this model more comprehensive. So we are able to integrate different estimations for emissions from aircraft. And for this paper, I want to, about 1 year ago, we had this thought, myself and Irene went together, and we say, one of the questions we want to pose to, one of the first questions we want to address in this research lab is that, how much of the total emission is caused by commercial aviation in Europe? And the follow-on question is that, how can we assess this emission using fully open data and open models? And third is that, can we use a bottom-up approach? That is, by calculating individual emission from individual trajectory, and then sum it up and come to a conclusion of the emission over the Europe. And the last one will help you to make the better use of $1 billion. That is, how can this emission be associated with a societal cost in terms of negative environment impact and degradation in air quality over the Europe? So with that research question in mind, I would like to guide you through some of the processes we did in this research. So of course, everything starts with OpenSky. As most of you probably know, the data that we use is OpenSky state vector. And we access this OpenSky state vector with the impeller share. There is a small tool that I wrote a few years ago called PyOpenSky. Well, it was called PyModS OpenSky. It's too long, and I short it back, say PyOpenSky. So what we did is I would take a 15-minute sample of all the flights over the Europe for the first 4 months of 2020. And we collect about 30 giga of data stored in packets. So it's a very compact way of storing data. So, and thanks to our dear colleague here, Xavier, I was able to very fastly process the data. 3 months of data, we probably used a few hours, process all this data, including the filtering, interpolation, resampling, and we get a 40 gigabyte of data. Thank you for the extra 10 giga. So we have a 40 giga of data, consists of all the trajectory of the Europe sampled at 15 seconds per second, filled with a gap field. Then we use it a fuel estimation from OpenAP to get a fuel consumption. And then we do the estimation of the emission based on different flight conditions. It sounds easy, right? So we can, however, I want to show you an example, how does it work, right? So on this slide, on the left-hand side, you see the trajectory. Good, so it's one of the longest flight that you could see in Europe. And so that I took this example, I think it's one of the A320 or 0.737. So I'm not sure now. But on the right-hand side, you see it's altitude, speed, and vertical profile. So this is what we get. We all know that we can get very easily from OpenSky Sky Vector. And the next part is to do the fuel estimation with the data that we have. So I want to ask a quick question in the audience. What is missing here? What is the parameter that is missing? The mass, aircraft mass, right? There are two ways to deal with mass. So there is the Monte Carlo way approach. So we generate a random mass from a distribution, let's say a normal distribution or skew distribution based on the takeoff weight, or the lazy approach, which is X% of the maximum takeoff weight. And I want to take off my scientist hat off a little bit, and I want to put my engineering hat. And many times, a good engineering is also a lazy engineer. Yeah. So I'm gonna take the lazy approach. So I want to take a certain percentage of aircraft mass. So in this research, what we look at is we take a 60%, 70%, 80%, of 90% of the maximum takeoff weight of all the aircraft at each trajectory, and we'll calculate the fuel consumption. So how we do this? So first we have all these 4 parameters: the aircraft mass. The small font here are the maximum takeoff weight. I'm also a bit ashamed of this approach, so that's why the font is small. And then you get the speed, you get vertical rate, you get aircraft drag polar. So here you can compute the net thrust of aircraft. On the other hand, we have a thrust model, open thrust model from the literature, allow us to calculate the maximum thrust at a flight level. So you have a net thrust, you have a maximum thrust at the flight level. What you get is a thrust ratio. And if you have been studied the emission data bank, you know that with the thrust ratio, you could estimate the emission. However, that is only on the ground conditions. So at a different flight level, the result will be different. So we go through a altitude correction to get the amount of emission that we want for the specific altitude. And then we got a free flow for the flights. And that is a complicated process with OpenAP, just one line of code. You can do free flow, en route, give the parameter, all done. And then let's go back to the example that I show you. So you can see that the mass actually is a very important indicator here. So for this single flight, if you vary between 60% of maximum takeoff at the start or 90% of takeoff weight at the start, there's a huge difference in the fuel flow during the whole flight. This is integrated at each time step at 15 seconds. So you can see that by aggregating this variance among all the hundreds of thousands of flights, there is a huge impact on how the emission can be calculated. So this is, I want to pay a special attention because this is one of the key uncertainties in this type of estimation. And now we have the fuel flow of each individual flight. Easily, we can get a CO2, water, SOx. Why is it so easy? Because they are linearly correlated with fuel flow. They're either too big, for example, CO2 and water, they are very high, one of the highest emission particles. And SOx is very small. So we normally assume a linear relationship. For the other ones, for example, NOx, carbon monoxide, hydrocarbon, they are non-linear. And I also adapt models from ICAO engine data bank, Boeing fuel flow method too, to make this process possible. So we do correction according to flight conditions, altitude, to make this calculation possible. All in all, you have another few line of code. Each line of code allows you to compute a emission at a certain flight condition. Noted that the final three has a correlation with the speed and altitude differences. So let's go back to the result. This is what you see. Yeah. So if you look at CO2, water, SOx, they are linear to whatever you see on the top, the red figure. And if you look at the others, they're different. Yeah, they're apparently more non-linear. And please note the unit difference. The first one is kilogram per second. The rest three is gram per second. So now it's time to bring all the trajectory together. This is figure. You see a aggregation based on the geographic grid. I also want to shout out again to Xavier for this amazing tool, Traffic, allow me to do this rendering and also the binning of this data very easily. The black boundaries are the region where the data are collected. This is a region that we took that to calculate it. You see that already there's some regions we cut off. So take that into consideration when I show you the final result. And what we can do is this, it's very interesting. There are a lot of possibilities to inspect. So one of the first things we do is that we look at the airlines, who is the biggest emitter. Of course, there is a lot of uncertainty here. There inaccuracy I will mention, but you can see that they're major emitters, I think 40 or 50 emitters here of the aviation. And the first one is the total distant flow for 1 month. And the second one is a CO2 that emitted from all their flights. And third one is divided by the kilometers flown. However, the last one cannot be used as an efficiency measure. I have to stress that because airlines have different fleet configuration. To further analyze the fuel efficiency, we have to divide by the fleet configuration, the number of seats. So this one is not a rule for measure the airline performance of a fuel efficiency. Hope anyone from airline will not sue us. Anyway, so this is interesting statistic we can get from this by aggregating data according to airline. We could also do aggregation by fear, right? So we have the fear information. Again, thanks to the traffic library, we can very easily bin it with a fear. And you can see the top emitters here. Those are the top emitters simply because there are more flights flying over these regions. And this is for the January of 2020. Another thing you can see is that we can bin it by altitude. The black bar you see this is each of the bins is the uncertainty indicator that it causes solely by the mass uncertainty. You see that actually the NOx has a really high uncertainty here because NOx is directly related with engine operating temperature, and depending on the mass of the aircraft, the engine operating temperature can change quite a lot. Then you have a much higher variance in the NOx as well. And keep in mind about the NOx in your mind, because this is one major uncertainty later on again in the cost estimation. So why January 2020? Why could I show you the rest of the month? So here is what you see, what happens in 2020. So the first 3 months of the 2020 in Europe was still okay, business as usual. But in April, something happened, we all know. That's why we couldn't meet each other in 2 years, almost 2 years. So the COVID happened. And what happens here that we have almost a daily average of 0.3 billion kilogram of emission of CO2, suddenly becomes only 0.05 billion kilogram. I wanted to stay here a little bit because this graph can tell us a lot. And there's a lot of different voices on how we can make aviation more green, more sustainable. So one of the mainstream is that the future lies in new type of technologies. For example, hydrogen, SAF, new aircraft. However, the operation optimization is only marginal, right? But however, what we see here is that operation optimization do matters because if you reduce operation, there is significant decrease in the CO2. And any bit of the operation reduction helps. Yeah. So the same thing you can see that is for the other type of emissions. Please note that the Y scale is in logarithm scale. So finally, the $1 billion question. Are you ready for it? So before that, I want to quickly go through this table. It's boring. So you have to notice that different emission species have different effect on the climate cost and air quality cost. So SOx and NOx is good for the climate because it cool the earth. Is it bad for the air quality? Well, because it's damage your health. So this is one of the research my co-author Irene Deducci is involved a few years ago with her co-authors, and this kind of parameter has been quantified, and so we plug in those numbers with all the CO2 and other type of emission we got. So this is the cost we have. So the climate cost probably stays about 10 million. The air quality cost stays about 60 million. That's per day. Yeah. So the environment bill for 1 month is about $2 billion. That is the calculation. So unfortunately, you're still far away, and you need around 1 more billion to pay the bill. Anyway, so the story is not over yet, because if you look at the y-axis, it's quite large empty spaces. There's a reason, because the uncertainty lying in this cost model, and there is large uncertainty because the effect of those costs are not very well understand, and has to be researched with future research. And I hope we will be able to contribute this part of the research in our future. And I want to, especially for my co-PI, Irene, she's working in this direction. So please keep an eye on our research. So as I said, that my scientist hat was off, engineering's hat was on. Now I want to put back on my scientist hat. I want to be critical about our approach. So we only have data about above flight level 100. We only have 50 most common aircraft types. This is 90% of all traffic, and we do miss air coverage in some countries. And OpenAP is also inaccurate. At low altitude, there is some uncertainty. Yeah. So I want to do I also want to shout out to Lauren Laluc from Thales, who kindly provides this sample anonymized data for us to check. And you see that again, there's a huge uncertainty in the mass estimation. So also, by the way, the OpenAP has a new website if you want to check out. Finally is the environment cost. There's a lot of uncertainty in the modeling chain. Just want to throw some jargons here involving social modeling, economics data from other domains, and Monte Carlo simulation. So, and then there's a huge impact about the contrails, which is not taken into consideration. To fly higher doesn't mean it's better, because higher you are, the contrail has worse effect for the climate. So there is a lot of research has to be done in this domain to make a fully concise conclusion. And also the emission that are not considered in this, just because the OpenAP model is not ready yet. So the final takeaway is that the monthly bill for 1 month is 2 billion, or somewhere between 500 million or 4 billion. With that, I want to conclude my presentation, and I will be happy to answer your questions.
Excellent, Junzi. That was quite a spot landing.